Bonding videos 9 through 11 focus on bonding theory of different types. So it's going beyond what we've talked about to really get into the explanation. So Lewis structures and Lewis theory focus on how many electrons there are, where they are, and if they're involved in bonds or not, but not really describing what it means for those electrons to be bonding. So we use Lewis structures. We can know if there's single, double, or triple bonds. We can know if there's lone pairs. But that's kind of all that theory does for us. The Vesper theory focuses just on shape. It is based upon the fact that electrons repel each other. They want to be far apart. And we kind of took that as an assumption that electrons are going to be far apart. But how can the electrons get to that position? We've talked about with individual atoms, we have atomic orbitals, we've got sublevels, we've got levels. Well, how can that connect with those different locations we see for the Vesper model, and how does that connect to the single, double, and triple bonds for Lewis structures? And that's where valence bond theory comes in. It's an explanation of bonding that connects to quantum mechanics, or connects to a similar idea of the atomic orbitals, that there's regions where the electrons occupy, and those are either between atoms, if they're bonding regions, or they're in other specific locations in space, if they're lone pairs. So it kind of brings together Lewis's theory with the idea of atomic orbitals, and it allows us to understand why the shapes are what they are from Vesper. So if we have two hydrogen atoms, we've got 1s and 1s, single electrons there, and we're going to start with hydrogen because it's the simplest atom, and therefore H2 would be the simplest molecule. Well, these are occupying space around the atom, and as we get closer and closer, and we can even look at this picture down here to remind ourselves of this, as we get closer and closer, there eventually starts to be some attraction between the protons here and these electrons, the protons here and these electrons, but they have to get close enough. So there's a certain distance where those attractions are maximized, or a certain position where instead of these electrons being randomly on any side of this, it's more likely that that electron is going to be found in the position between these two nuclei. And it's more likely that this second electron would also, because of the attractions, be in the position there. So we start to have some overlap of these orbitals, and that's what our covalent bond is. The 1s orbitals overlap. Now the electrons concentrated between the nuclei. But because they repel each other, they're not going to be directly on top of each other. We have a new kind of orbital, or a new region where they're most likely to be found. They're not necessarily always going to be exactly right there between the nuclei, and they're not always going to at every single moment be there, but they're going to be where the attractive forces, which is what this side of the graph, I'm jumping down to the graph here, where the attractive forces can be maximized at a distance where the nucleus is attracted to the electron, this nucleus is attracted to the electron, and the electrons back to those nuclei, where we maximize that without getting them so close together that the electrons repel, and especially the nuclei repel. So that's a pretty simple drawing there when we think of it in terms of hydrogen, but as we go to more complex molecules or slightly larger molecules, the same idea happens. Hydrogen fluoride, which is what this picture is, has the same idea. We've got a hydrogen electron in the 1s orbital. For fluorine, fluorine has the electron configuration 1s2, 2s2, and then in the 2p sublevel, the first orbital's full, the second orbital's full. So we have, as it says here, one orbital, or is it the empty? I guess it's not so much the empty, it's the one that's not completely filled. So it has one electron there, and that one electron, just like the electrons up here, we've got those, they're going to occupy the space between the two nuclei. That's their most likely position. So if we've got an electron there, we can get the attraction from this nucleus to both electrons, this nucleus to both electrons, and then fluorine's inner electrons, their core electrons, the s and the p's, are going to be somewhere else. as it's set up here, non-bonding electrons have a specific region in space, but we're focusing on the fact that they're there, and in each of these pictures you see an up and a down. So we have them paired up. So just like with atomic orbitals, they're occupying the same space, and because they're occupying the same space, they have opposite spins. And magnetism is proof for these opposite spins. If you go back to the atomic videos, that's how we know that there has to be something to do with spins, that electrons have to spread out equally, because we have all those electrons either canceling one another out by spinning in opposite directions like they are here, or in half-filled orbitals all spinning the same direction and making something magnetic. So that was hydrogen. This is HF. So down here it's F2 with the exact same idea. We still have most of level 2 filled, but that last 2p has one electron in it. When the 2p from one fluorine overlaps with the 2p from the other fluorine in the same axis, and here it's drawn in the x-axis, we put those two electrons, their concentration of highest density is between the two nuclei. Once again, we are maximizing the attractions, minimizing the repulsions, and the electrons aren't exactly between those two nuclei at all time, but that's where they're spending most of their time. So in all three of these scenarios, and scroll down just to see this a little bit more, the electron density, or the most likely position to find our electrons, is kind of that place right there, or right there. The space between the nuclei. And a term we can use for that would be along the internuclear axis, which would be a line connecting the two nuclei here. So that would be the internuclear axis in each of these cases. So the axis on which the nuclei are drawn. In this and this, it would be labeled as the x-axis, but it doesn't have to be. So when you have your electrons in between your nuclei, is what it means to say concentrated along the internuclear axis, we have what's called a sigma bond. All single bonds are sigma bonds because the electrons are directly between those two nuclei. But once we start to have double and triple bonds, and we've already got a place where some of the electrons are, we start to go outside that internuclear axis. And we're going to talk about that as we get into orbital hybridization and some other bonding theory. But just some basics here, or just a quick recap, because this is a short one, is thinking about we're going beyond Lewis structures and VSEPR, not just what shape do we see or what type of bonds do we have, but how can the electrons actually get into those locations. And it has to do with overlap of atomic orbitals, creating new orbitals that make a region of concentration of electron density, or having a new place in space where those shared electrons are most likely to be found. All about maximizing maximizing attractions by getting to the right bond distance while minimizing repulsions by not being too close. And as we start to describe double and triple bonds, and we start to connect this a little bit more into VSEPR, we'll take this valence bond theory and add in an idea of orbital hybridization as we go to video 10.